Good morning, everyone. Welcome to the BRO seminar series. It's my pleasure to introduce our today's speaker, Dr. David Eaton, who is talking about seismicity induced by the development of unconventional oil and gas resources. Let me give you a brief introduction about Dr. Eaton. Dr. David Eaton was appointed 2015 to 2020 as the NSERC Chevron Industrial Researcher in microseismic system dynamics in the Department of Geoscience at the University of Calgary. Together with graduate students and postdoctoral fellows, his work focuses primarily on advancement of research, education, and technological innovations in microseismic methods and their practical applications for resource development, with a secondary focus on the deep lithospheric structure of continents. In 2007, he rejoined the University of Calgary as the head of the Department of Geoscience after an 11-year academic year at the University of Western Ontario. His postdoctoral research experience included work at ARCO's Research and Technical Services in Plano, Texas, and the Geological Survey of Canada in Ottawa. He has recently published a textbook on passive seismic monitoring of induced seismicity. His work was recognized by the 2020 J. Tuzo Wilson Medal from the Canadian Geophysical Union. So with that, I would like to welcome David again, and let me turn it over to you to start your talk.
Well, thank you for that kind introduction, and thanks for the opportunity to give this presentation. So there's been considerable interest in the topic of induced seismicity during the last decade or so from academics, industry, regulators, and the public. The presentation I'm going to give today is fairly high level, so it's an overview, and the primary focus is on induced seismicity that is triggered by hydraulic fracturing. In case anyone's wondering, when I'm talking about unconventional here, I'm talking about shale gas and tight oil that requires hydraulic fracturing completions in order to produce, and it's not the Canadian oil sands that I'm talking about. So here's a outline for my presentation. I'll start with a brief history of injection-induced seismicity. It dates back to the 1960s. And then show our current global occurrences as they've been published, talk a little bit about the activation mechanisms for faults, and I'll finish up with a little bit of a discussion about what we know about the maximum magnitude of induced events. Most of what I'll be presenting today is published in 3 recent review articles. One of them is in Nature Reviews of Earth and Environment. There's also a paper that recently came out in Reviews of Geophysics. And I've got a chapter that's in press in a book by Cambridge University Press. So all of the references that I'm showing will be taken from these review articles, and I'd be happy to share these with anyone if they're interested. So let's get started. As I said, our understanding of injection-induced seismicity dates back to the 1960s. And what to this day is one of the clearest examples of a correlation between injection and seismicity is from the Rocky Mountain Arsenal seismicity sequence. This started in 1962. So the US Army started to inject chemical waste fluid into Precambrian basement rocks underneath the Denver Basin. You can see in the top graph the injection rate, the monthly injection rate. Below that is shown the seismicity rate in the area. Very clear correlation. There was a pause in activity for a while, and then injection started up again just with a gravity drive. And then it was pumped once again, and that led to a further increase in seismicity. And due to concerns about the seismicity, the pumping was stopped in 1966. And you can see on the left, so the USGS had deployed some seismometers in the area. So these are some precise locations. They appeared to delineate a possible fault in the area. And indeed, in 1967, there were 3 magnitude 5+ earthquakes in the area. And these earthquakes far exceeded the likelihood for earthquakes of that magnitude in this area, and represented kind of the first well-documented case of injection-induced seismicity. And the theory at the time was that this was related to the so-called effective stress hypothesis. So this is actually a very simple model to understand. Effective stress is essentially a reduction in the normal stress through the presence of pore fluid pressure. So it's easy to represent using a Moore diagram, which is what you're looking at here in a sketch form. So here we're just plotting the normal stress on the horizontal axis against the shear stress. So the shear stress is promoting slip on a surface, and the normal stress is acting as a clamping force. There's failure criteria such as Moore-Coulomb, which divides this domain into a frictionally unstable region and a frictionally stable region. Given a state of stress, any orientation of fracture or fault will plot within the shaded region, which is shown here, that's bounded by these circles. So the basic idea is as the pore pressure is increased, it shifts the Moore diagram to the left on here because of the reduction in effective normal stress. And given enough increase in pore pressure, we can slide a fault into the frictionally unstable regime and trigger slip on a fault. Now, although there was very strong evidence from the Rocky Mountain Arsenal earthquakes that this is what was occurring, it wasn't a controlled experiment. And so there was a follow-up study that was undertaken at the Rangeley Field in Colorado. So this was a collaboration between the US Geological Survey and Chevron. So this is a conventional oil field that was undergoing enhanced recovery by water flooding. The operator of the field had noticed that there was some weak seismicity that was occurring during the enhanced recovery operations. So the USGS came in, installed some seismometers so they could get a better recording of induced seismicity in the area. They also did some laboratory geomechanics and hydraulic fracturing in order to estimate the state of stress. Based on that, they calculated a critical pressure which they felt was necessary to activate faults in this area based on the effective stress hypothesis. And then they underwent hysteresis, where they lowered and raised the pressure in the reservoir to observe the seismic activity. And this study ultimately ended up as a very strong validation for the effective stress hypothesis. In fact, the leaders of this study had a bold conclusion that earthquakes can be controlled wherever we can control fluid pressure in a fault zone. So this was the story in the 1970s. Now, if we fast forward about 30 years, the same kind of operation or the same kind of scenario was unfolding, but at a much bigger scale. And I'm sure people in the audience here are quite familiar with this. So this is in the state of Oklahoma. Due to injection of salt water, brine that is co-produced with oil in this area, there was a pore pressure increase in seismogenic region and a consequent increase in the rate of seismicity in the area. These diagrams are taken from a Science Advances paper by Langenbroek and Zobak. On the left, you can see graphs. So there's both a linear and a logarithmic scale showing the rate of seismicity in this area. And it starts to depart from the tectonic background rate in about 2009, producing a lot of earthquakes in central and northern Oklahoma. And on the right, you can see the total injected volume into the Arbuckle group, which is a karst limestone which unconformably overlies Precambrian basement in the area. And this is compared with the pattern of seismicity, and there's a very clear correlation between the two. Now, contrary to a lot of media reports, this is actually not primarily due to hydraulic fracturing. This is disposal of massive volumes of brine, which is co-produced with oil. So the oil fields in this area generate a lot of brine. It's highly saline, And as a disposal procedure for that, the saline brine was pumped into this highly permeable formation. But once the pressure in the formation had diffused into faults, which are in hydrologic contact, so these are faults in the underlying crystalline basement, then we started to see seismicity in this area. So this set of maps just gives you a little bit of a spatial reference, a spatiotemporal reference for how this seismicity evolved from 2008 to 2019. And so you can see on here, initially the activity was mainly in central Oklahoma, but by 2012 and going onwards, it had spread northwards into the northern part of the state, as well as parts of southern Kansas. There are a couple of other notable areas of seismicity that are marked on these maps. So that includes seismicity around the Cogdell field near Snyder, Texas, and then seismicity in the Dallas-Fort Worth area, including the Azle cluster. So I'm not going to be talking about these in my presentation today, but hidden in the background of all of this seismicity was seismic activity, which is now known to be related to hydraulic fracturing. And that's especially in these scoop and stack areas of interest that have been defined by the Oklahoma Corporation Commission. So they're outlined here on this map, and I'll be talking about those a little bit more later. But back to the saltwater disposal related seismicity, much like the situation in the Rangeley field in Colorado, as the pressure was increased and then started to subside, we saw a corresponding pattern of seismic activity. So this graph, also taken from Langenbroek and Zoback, is showing the monthly injected volume with the blue curve. It started to go down both due to a drop in world oil price as well as mandated injection reductions. The seismicity magnitude 3 and above is shown with the green curve, and you can also see upticks in seismicity due to aftershocks of some of the larger events. And then in the red dash curve, you can see the calculated pressure rate 3 kilometers below the injection, which is about on average where the seismicity is occurring. And there's a very good agreement between the two. And because of the reduction in pressure, we're starting to see a waning of seismicity in the area. Now, I'd like to go back just a bit to 2012 and a report that was released by the US National Research Council. This was a report on induced seismicity from energy technology. It was commissioned by the US Senate over concerns from events such as seismicity in the Dallas-Fort Worth area, as well as seismicity in Switzerland from geothermal operations. So the map on the left is showing a summary of what was known at the time when this report was first released in July of 2012. And so the seismicity here is broken down by the type of energy activity that was associated with these events. And you can see that the symbol size is scaled by magnitude. The one that we're interested in is hydraulic fracturing for shale gas. There's only one point on this map which is related to that. So that's a very small event near Blackpool in the UK that took place in 2011, about a magnitude 2.3 event. The basic model is shown on the right. This is from earlier work published by Sean Maxwell and others. This is from microseismic monitoring. So these are much smaller events, generally below magnitude 0. But you can see based on geophones, which are deployed in a well close to the injection, we can map a hydraulic fracture that intersects a fault. So then this will lead to a pressure increase in the fault and then triggering slip on the fault and activity along there. Now, I said the NRC report was released in July of 2012. Had they waited one more month to publish the report, they could have made use of 38 additional events, which were noted by the British Columbia Oil and Gas Regulator in the Horn River Basin. So that's in the area which is shown by the pink star on the map. So in the Horn River Basin, the industry was drilling into the Devonian Horn River Group shales. There were massive operations underway, and it was realized that there was a spatial and temporal correlation between a significant uptick in seismicity and hydraulic fracturing operations. So incidentally, the photo on my title slide was taken from a 2011 hydraulic fracturing operation in the Horn River Basin. So it's located in northern Canada near the border between British Columbia and the Northwest Territories. There were two clusters of seismic activity that were observed during this period of time. One of the challenges was that during the industrial activities in the Horn River Basin, there was only one public seismograph station which was operating. That was at Fort Nelson, British Columbia. So that was a bit of a challenge, but scientists within Canada's Natural Resources Department have done a lot of work on this, and they've noticed some interesting correlations. One of their findings was that it appeared that seismic activity was confined primarily to periods of time when multiple operators were injecting at the same time. So it appeared as though there might have been some cumulative effects that were at play in this area. So I'll switch and now mainly talk about hydraulic fracturing induced seismicity. You can see in the map on the left, both saltwater disposal and hydraulic fracturing events are shown in the blue and red symbols. This is the situation as we know it today in 2020. So this is based on the HiQuake database. And this has been plotted on top of a map of shale basins that have had resource estimates based on EIA reports. So you can see there's quite a number of shale basins where hydraulic fracturing activity is either occurring or could occur in the future. And we now know that there are events up to moment magnitude 5.2 that have taken place that are attributed to triggering from hydraulic fracturing. And this compares, if you look on the right, the 2012 map where there was only a single event, a magnitude 2.3 event that was known at that time. So I'm going to go and talk about some of these. I'll be talking mainly about basins where there has been a significant amount of unconventional development. So these are among the most active basins in the world. I'm not going to be talking about the Permian Basin in this presentation, but we will look at the Eagle Ford, the Woodford Plays in Oklahoma, as well as ones in Canada, such as Alberta and British Columbia, as well as the Sichuan Basin in China. Now, just a bit of a primer here for those who are unfamiliar with focal mechanisms, because I'll be showing some of them in this presentation. So this is taken from the World Stress Map, and I've plotted focal mechanisms, and they're color-coded based on the diagrams which are shown at the bottom of the map. So this is representing the Andersonian faulting model, where there are three distinct primary faulting mechanisms: normal faulting, which you can see with this type of focal mechanism; strike slip faulting, which has a characteristic type of focal mechanism where you can see four different quadrants; and then reverse faulting, which is represented by a mechanism here. Now, it turns out that many of the induced earthquake events in these shale basins have a strike slip type of mechanism, but we do also see normal faulting and reverse faulting. So it depends entirely on the stress regime where these are occurring. So I'd like to start by talking a little bit about Oklahoma. As I mentioned earlier, the vast majority of induced seismicity in this area has been tied to saltwater disposal, but there has been an underlying recognition of events which are actually related to hydraulic fracturing operations in some parts of the basin. So, so you can see an outline for an area of interest, which was identified by the OCC in 2016. And on the right, you can see seismicity, which has been documented in papers. The Skumal et al. Paper used a technique called template matching, where they took some known templates and then cross-correlated that, and were able to find many more events. The Shimada et al. Paper is work where there's cross-referencing done starting in 2016 between the hydraulic fracturing permit applications and seismicity. Both of them show a considerable level of induced seismicity activity, especially in the scoop and stack area, where some counties show a very high fraction of hydraulic fracturing wells associated with induced events. To date, the highest magnitude event in Oklahoma from hydraulic fracturing is magnitude 3.9. That was July of 2019 in Kingfisher County. The Eagle Ford play has recently been studied. You can see here a map that's taken from a paper by Fasola et al. In 2019. Again, these authors used a template matching in order to extract lower magnitude events to generate a more complete catalog. They found a significant increase in seismicity rates in the area of Eagle Ford shale play development in South Texas. So in 2018, seismic activity was more than 33 times the background seismicity rate. The largest event took place in 2018. It was on a normal fault in the Carnes Trough. It measured magnitude 4. And that to date is the highest magnitude event which has taken place in the United States that is related to hydraulic fracturing. That event occurred about 10 kilometers from an event from 2011, which measured magnitude 4.8. So what it appears is that hydraulic fracturing for the Eagle Ford shale in this area is activating some normal faults, which have already experienced some historical seismic activity. Now, moving to the Sichuan Basin in China, these are results that were published in SRL in 2019 by Li et al. This work is from the Changning Shale Gas Basin, which is in the southern part of the Sichuan Basin over here. Here, the industry is stimulating, they're drilling and stimulating the Long Maxi Shale, which is a Silurian unit at 2 to 3 kilometers depth in this area. But there is a fair amount of structural complexity. The overall setting here is a broad syncline which is being developed. The largest hydraulic fracturing induced event, which has occurred to date, took place in this area during hydraulic fracturing operations in December of 2018. Local magnitude 5.7, moment magnitude about 5.2. This event occurred at about 3 kilometers depth, so about the same depth as the hydraulic fracturing. It produced strong ground motion within the area, which is outlined in the black dashed curve. The closest village is located here, and there were a couple of areas of landslide activity that were triggered by this event. And 2 weeks later, there was another hydraulic fracturing induced event that took place about 8 kilometers away from this one. So I'll now turn to some work which I've been involved with in Western Canada. We'll look first at the Montney play, which is a Triassic siltstone. It covers an area which is roughly equivalent to the Eagle Ford play in Texas. And it straddles the border between two provinces with two different regulators, Alberta and British Columbia. It turns out that for this play, the BC regulator drew the short straw because to date, all of the induced seismicity has taken place in the northern and western parts of the Montney play entirely in British Columbia. So you can see from the graph on the right, cumulative number of events greater than magnitude 2.5. The seismicity started to exceed the background rate in this area during the development of the Horn River Basin, but this was quickly surpassed by the development of the Montney shale play in this area. We have a paper that actually just came out last week that's from the northern part of the Montney, so within this area, or close to this area of increased induced seismicity. And for this, in this paper, we were able to make use of high resolution 3D seismic data from the oil and gas industry, where we could map out faults that are part of a buried thrust belt. So these are Laramide age blind thrusts, which are in the foreland of the northern Canadian Rockies. So you can see these thrusts sole into a basal décollement and then terminate upwards into fold structures. The fault F4 in this diagram is more subtle than these, but is the one that was activated during hydraulic fracturing. Another important unconventional play in Western Canada is the Duvernay carbonaceous shale play. This is located in the province of Alberta. And you can see here on this map the distribution of the play. It covers an enormous area. And on the right, you can see the cumulative number of events. This is color-coded to the color of the symbols shown on the left. So this purple color is part of the Montney trend that I was talking about before. The Duvernay play producing events significantly in excess of tectonic background rate, but several other areas of induced seismicity that have other causes besides hydraulic fracturing are shown in this gold and blue color. Now the Duvernay shale is an organic rich fine grained rock that was deposited at the same time as the growth of these late Devonian Leduc reefs. And the Duvernay actually forms the source rock for some very large conventional oil pools in Western Canada that are hosted in Leduc reefs. Now these reefs form a number of linear chains, such as this one that I'm pointing out right now. And it's long been suspected that these linear reef chains were influenced by basement tectonic activity. So there's underlying faults in the Precambrian basement. The Precambrian basement is 400 to 500 meters deeper than the reefs, but subtle features in the basement are what influence these reef trends. But now the shale development is taking place adjacent to the reefs, and we can see here a number of strike slip events which were taking place there. The most recent one was in March 2019. It was a magnitude 4.5 event, which occurred near the city of Red Deer. So we published some work on this in Science in 2016. This was a follow-up to a January 2015 magnitude close to 4 event. We made use of a dense seismograph array and did precise relocations in order to bring out or to highlight the seismicity within 2 fault strands that we call the east fault strand and the west fault strand. Here the hydraulic fracturing was a zipper frac operation between 2 north-south horizontal wells, and this is an east-west profile. And what our results indicated was that the fluid injection into these horizontal wells may have inadvertently pressurized a steeply dipping fault that extends down into the Precambrian basement, as you can see here. What was interesting is that the east strand, which was farther from the wells, ceased activity almost immediately when hydraulic fracturing ended, whereas the west strand showed latent seismicity, so persistent activity, and the largest event took place 2 weeks after the completion of hydraulic fracturing in this area. So our interpretation from this paper was that in accord with a lot of models that existed at the time, that there were basically 2 mechanisms for fault activation from hydraulic fracturing: an increase in pore pressure or a change in the stress conditions on the fault, which is communicated through the medium. This is a paper that was published more recently in and Science Advances. This is for a event that took place 1 year later in 2016, but was quite close by. We had very good seismic data or seismicity data from the area. It allowed us to constrain the hypocenter of this fault as being actually above the injection zone within a very massive competent carbonate unit. And when we looked at the depth distribution of seismicity and microseismicity from this event, it's concentrated at the boundary between the shale layers here in the Ireton Formation and below, and then these much stronger carbonate layers above. This was accompanied by some petrophysical work, which I don't have time to go into right now. But to cut a long story short, this allowed us to develop further another hypothesis, which is that hydraulic fracturing is pressurizing faults, leading to aseismic slips, so very slow creep on the faults. But as this creep is occurring, it is loading other parts of the fault. So the stress load, rather than being through the medium, is carried along the fault and ultimately leads to dynamic rupture. I'm not going to have time to cover these other complications. This slide is simply making the point that once we take all the information we have about layering of some of these properties, such as BO parameter, we end up with depth-dependent stress conditions, which are a complication. And this is some really interesting work done by Hess Corporation in the Bakken play in North Dakota. And very briefly, what they did is they drilled a set of wells, but only completed one of them in the first year. They came back a year later and hydraulically fractured the other wells. And to their surprise, they recorded a lot of seismicity along the well that had been completed the previous year. So they came up with this model based on poroelasticity of depletion-induced microseismicity. And the idea here is that as the pore pressure is reduced, it actually increases the deviatoric stress. So it's exactly counter to the effective stress hypothesis. And again, this is just an example of some of the complications that have to be dealt with in order to truly understand the risk. So I'd like to conclude with just a few words about quantifying the maximum magnitude for hydraulic fracturing induced earthquakes. And getting a maximum magnitude is important for a number of reasons, including engineering design and scenario earthquakes, as well as probabilistic hazard assessment. In my experience dealing with the media, talking about hydraulic fracturing induced earthquakes, is usually what I would really like to talk about is all the cool scientific research that we're doing. But typically the line of questioning and the general interest, people want to know what was the magnitude of the event. Oftentimes we get different magnitude estimates from different agencies. And so they want to know why the magnitudes differ. And then what is the biggest quake possible is one of the big questions that always seems to come up. So on that topic, there are a number of different models that exist. Art McGarr with the USGS published a widely used model that relates the maximum seismic moment to the injected magnitude via the shear strength of a fault. So you can see from his compilation, the green symbols that are shown here, largest one in this publication was an induced event at Prague, Oklahoma. And they seem to agree with this limit. Now, since seismic moment is related to moment magnitude, with this formula, the slope of this in the magnitude versus logarithmic injected volume is 2/3. And you can see there's a series of assumptions that were made. Now, there are a few issues with this. We need to really understand the cumulative effects, and there have been plenty of discussions in the literature about the Prague earthquake. How do we actually calculate the net injected volume? There's also examples of hydraulic fracturing induced earthquakes that unambiguously exceed the McGarr limit. There's also the notion, and this was discussed in a paper by Van der Elst and others, that ultimately if earthquakes are occurring on pre-existing faults, then the maximum magnitude may only be limited by the fault dimensions. So Van der Elst introduced a statistical model, and they argued that the maximum magnitude actually follows a trend which is governed by the so-called B value. So that's the slope of the magnitude frequency distribution. It's typically close to 1. And then another variable called the seismogenic index. And in their statistical model, they were able to come up with 90% confidence limits, which produces this kind of corridor of expected probability for events. And they argued that it actually fits McGar's data better than the McGar relationship. But it still leaves unanswered these anomalous events that are shown here. And a very similar relationship was developed from a different basis using rock mechanics by Gallus et al. In 2017. So in our recent review paper, we talk a little bit about the concept of runaway rupture, which is what occurs when the slip area on a fault extends beyond the pore pressure perturbed region. And in that case, the maximum magnitude may actually only be limited by the fault area, which is exceedingly difficult to estimate in advance. I showed you an example of 3D seismic data from the Montney play, where we have very high resolution data, and there's a possibility that we can estimate some of these things. But many of the induced events, including the largest event so far in the Sichuan Basin in China, occurred on faults that weren't previously known. So this creates certainly an issue. So I'll leave you with these takeaway points from the presentation. Since 2012, we've now recognized induced seismicity triggered by hydraulic fracturing in unconventional basins around the world. The events seem to be similar to their natural counterparts in a number of respects, including the source characteristics, magnitude frequency characteristics, and the ground motions, although induced events tend to be shallower. So for the same magnitude, they tend to produce stronger ground motions in the immediate vicinity. Models for how faults are activated during hydraulic fracturing are important to understand in terms of developing risk mitigation strategies. So they include a pore pressure increase, a change in fault loading conditions, and some new evidence that we have for aseismic slip, which is loading other parts of a fault. In the case of contained rupture, so the opposite of runaway rupture, there are several models that predict that the seismic moment scales with the net injected volume. And an advantage of those models is that implies that it's controllable. So if we limit the net injected volume, we can limit the maximum magnitude of the events. But for rare cases of what appears to be runaway rupture, so slip extends beyond the perturbed region, the maximum magnitude, like natural earthquakes, may ultimately be limited by the fault area. So that concludes my presentation. Just some quick acknowledgements. A lot of the work that we've done has been supported by industry as part of the Microseismic Industry Consortium. Funding for this research has come from the Natural Sciences and Engineering Research Council in Canada, as well as the Canada First Research Excellence Fund. So I'd be very happy to answer any questions, or if people would like to email me, my email address is shown here. So thank you for your attention.
David, thank you very much for your interesting talk. It was absolutely a comprehensive review on induced seismicity in conventional reservoirs. So I see multiple questions in the chat box. The first one is from Mark Schuster. Mark, would you like to unmute yourself and ask your question verbally?
Yeah, happy to. Thanks, Lucy. Hey, David, that was really a great talk. Wonderful to get that overview. And I was just curious if there are any data from the fracking operations themselves where you see any indications from pressure drops or indications of frac pressure drops that would indicate communication with faults?
You know, that's a great question, and that's certainly what you would expect, because loss of fluid into a fault is problematic for unconventional development, even if there is no induced seismicity, because you're wasting resources pumping fluid into a fault. In fact, from my knowledge, which I can't claim to have a comprehensive knowledge on this, but it's more common that people see screenouts. So they see unusually high pressure prior to an induced event. But certainly that's something that the operators are looking for, is loss of fluid into a fault. But I haven't actually seen that specific indicator mentioned in the work that I'm familiar with.
All right, there is one other question from Iasen Grigoratos. I hope I pronounce your name properly. So Iasen, would you like to unmute yourself and ask your question?
Sure. Thank you for this presentation. So I did read the recent paper about these thrust belts and these connections with aseismic slip. And I was wondering, you outlined several mechanisms. You mentioned some in the presentation: pore pressure increase, pore elastic stress coupling, and non-seismic slip. And a lot of the studies you mentioned link the probability of triggering earthquakes with injected volume. The larger the volume, the more likely it is to get earthquakes. Are all these mechanisms compatible with that hypothesis? Is only pore pressure increase related to volume increase? Just wanted to clarify this sensitivity with injected volume. We observe it in some formations, not in others. Does it have to do with the mechanism or not, do you think?
Yeah, thanks for the question. That's actually a very interesting question to pose. Yes, the correlation with volume is largely empirical. So, a number of researchers have documented this. We have a paper in Science that Ryan Schultz was the lead author, where he shows that statistically that there's a correlation with volume. Now, you can argue that volume would not only affect the pore pressure increase, but would also other ones. So a pure poroelastic model, the stress loading in the formation would scale with the injected volume. So that one would make sense. For the aseismic slip, it actually ultimately comes back to a pore pressure increase on the fault. But there's kind of a second step in the process. So we're driving the fault to slip. The amount of slip, aseismic slip, is related to the volume. And then the amount of aseismic slip is what loads other parts of the fault. So I think there's still, you can make strong arguments that all of the mechanisms could be linked back to volume. But there's still some indications that rate is important as well in certain areas. And so we're still trying to get a better understanding of how those two things play off against each other.
Thank you.
And the other one is from Peter Eikebel. I think Peter has a comment on slide 5. And Peter, you're welcome to unmute yourself and ask your question.
Good morning, David. This was an exceedingly clear overview. I really appreciate your talk and your presentation. The one part I would perhaps a little bit disagree with you. So you mentioned the poroelastic effects as being a somewhat different driver besides the Tesagi effective stress change. And we have done several fully covered poroelastic simulations for induced seismicity, where we try to separate those effects out. The way you write the effective normal stress law on the right side, I think is somewhat misleading, because you're lumping together the Tesagi effective stress law with the BO effective stress law. And for us who are interested in separating those effects, I would advise against that, because the Tesagi effective stress law, the parameter before the P term, is typically considered to be 1, but in our simulations for the BO effective stress law, we use an alpha that is somewhat less than 1. I see this frequently, but I think it's confusing a little bit the physics behind that.
Yeah, and yeah, thanks for pointing that out. Of course, this is highly oversimplified. I should have mentioned that. I was actually trying to harken back to the original concept that was proposed in 1959. So it's come a long way since then. And some of the complexities in poroelastic coupling, I think, are illustrated by the depletion-induced seismicity case that I showed earlier, where you're actually changing the deviatoric stress by producing events. And they also did a fully coupled poroelastic model to explain that. So it's definitely more complicated than shown here. This was kind of a very simplified model.
So we have a paper that Mari Haddad is the lead author, and he can tell you more about it. But we can show that the poroelastic effects are also significant for inducing hydraulic fracture-driven earthquakes. And that's work that hopefully will come out this year or early next year.
Yeah, I'd be very interested to see that.
Thank you.
All right. There is one other question from Jens Erikman. So Jens, you're welcome to unmute yourself and ask your question.
Hi, Dave. I hope you can hear me. Thank you.
Yeah, I can hear you fine. Yeah, and I'm just reading your question right now in the chat window.
Yeah, that's right. So this is more of a rhetorical question, I imagine. I don't think anyone has solved this, but it's an important one, I think. You were talking about the importance of, well, some of the problems with the models relating injected volume to magnitude. I fully agree with the problems with those models. But a lot of the earthquakes that we have seen have occurred on faults that were not known before, so their maximum sizes couldn't have been known in advance. So I'm just more rhetorically wondering what options we have then to think about maximum magnitudes in areas where you might not know what the faults are.
Yeah, no, that's really an excellent point. It's a bit paradoxical that oftentimes the induced events are occurring on faults that have an exceedingly subtle expression in seismic data. So seismically mappable faults, even if they're in proximity to operations, don't seem to be creating as much issues as the really low net slip faults that are hard to detect with seismic. And then this raises questions about how do you manage risk in a scenario where it's very difficult to confidently map these features in advance. So I think I can tell you a little about some of the directions that we're taking right now in our research. One of them is to sort of not necessarily try to map all of the faults in an area with seismic data, but apply sound structural geological principles. So characterize an area in terms of the types of faults which occur in that area. Quite a few of the ones that we're dealing with in Western Canada seem to be linked to flower structures. So we might have some underlying basement fault that produces this reactivated in the Phanerozoic. It produces these flower structures. We can't map every part of the flower structure, but we can say something about the structural setting and then apply a probabilistic approach to try to better understand the magnitude distribution. So there's kind of going back to structural geology 101, I think is one of the ways that we can do it. We've long had the notion as well that a critically stressed fault will have some kind of very localized stress signature because it is the fault itself is weaker than the surrounding rock, and so it sheds stress into the surrounding medium. It wouldn't affect the regional stresses, but in a very localized sense, there could be kind of a stress halo around a fault. And how could we detect that stress halo? Maybe using seismic attributes, maybe with well logged formation image logs and that kind of thing. But that's also a direction that we're trying to explore, which is a bit more kind of an explicit approach.
Just to thank you, and add one more thing about that is, well, maybe two more things, is the Pohang example, I think, is a good case of where knowing the historical upper threshold of magnitudes was helpful, would have been helpful for knowing what size earthquake would have been possible for an induced earthquake there. Of course, our recorded history is not necessarily long enough in most places. And as you do microseismic monitoring, I imagine would be helpful as well for delineating faults, but just a few ideas.
Yeah, no, thanks. Those are great points too.
The last question came from Alexandros. Alexandros, you are welcome to turn on the mic and ask your question.
Thank you, Sahar. Thanks, David, for the nice presentation. It was a very nice overview. In your recent paper with Ryan Schultz, you discuss about the Delaware Basin and the induced seismicity in the Delaware Basin due to hydraulic fracturing. What do you think about if it is the seismicity that is also partly due to saltwater disposal? What are your thoughts on this?
Yeah, I think that, so that's a great question. And I actually deliberately didn't include the Permian Basin in this presentation, partly because there are people in the audience who would know more about it than I do, and also because it is complicated. So a lot of these plays, there are competing effects from saltwater disposal and hydraulic fracturing. Undoubtedly, they commingle, so they influence each other. It appears empirically that some areas maybe the larger problem is the saltwater disposal, and in other areas the larger problem is fracturing. But there's no doubt that both of them exist together. I'm actually more familiar with the Montney play in British Columbia, where both have been documented. And the regulator there, the BC Oil and Gas Commission, is expressing confidence that they can manage the disposal-related seismicity, because in that case, the disposal wells are injecting into confined reservoirs. They monitor the pressure, and they place pressure cap on those, and then they have to stop injecting until the pressure bleeds off and drops again. And they found that strategy has been effective. They've had more challenge with the hydraulic fracturing, trying to manage that risk. So I expect there are similarities elsewhere with those kind of generalized observations, but I think the Permian Basin is a complicated one. And it also includes natural tectonic seismicity that Jens was mentioning too. So it's a case where you can draw from historical record of seismicity to better understand things like maximum magnitude.
Yeah, that's true. We also have a tectonic seismicity in West Texas. It seems though that mostly when the oil and gas activities increased in the area, we started having most of the recent seismicity. So the tectonic events has been more to the western part of the West Texas, and the central Delaware Basin and the South Delaware Basin is somehow mostly related to the oil and gas operations. Thank you for your feedback.
We got another comment from Mahdi. Mahdi, would you like to unmute yourself and ask your question? Mahdi, can you hear us?
Do you hear me now?
Yeah,
hello?
You're okay.
Hello.
David, thank you so much for this great presentation. I enjoyed it a lot. So my question is about Ear et al. Work that was published in 2019. You mentioned that there were a lot of earthquakes on the interface between the shale and the overlying carbonate rock. So there is a lot of studies on interface activation. So basically because of large mechanical property contrast, the interface can sleep. And then because of that, there might be some microseismic or large magnitude earthquakes that happen within the interface. So I was wondering if these events have been distinguished from each other, like the events that happened along the fault versus the events that may happen along the interface. So I see a lot of earthquakes right at the interface. I was wondering if these events can be distinguished or have been done.
Yeah, okay, well, again, a great question. I didn't have time in my presentation to talk about this, but the graph that's shown on the far right here is an estimate for the clay plus total organic carbon as a weight percent. There's been work from Mark Zobac's group, which shows that in areas where this clay plus TOC weight percent, so for shales, where that exceeds about 30%, then you expect it to behave with aseismic creep. So the rate state friction parameters would produce an aseismic creep. And that was one of the things that we sort of drew from. But you're absolutely right. Where we have a significant geomechanical contrast, in this case is between a fairly strong, geomechanically strong, massive carbonate unit and an underlying shale unit, so fine-grained shale with clay and organic carbon, then at that contrast, we might expect to see a concentration of deformation. And in fact, this is, my understanding is that there's been some cases of casing deformation in the area. They may or may not be connected to induced earthquake activity, but where we have these really strong geomechanical contrasts, that's where this seems to be problematic based on kind of anecdotal evidence that I'm familiar with. And also we sometimes see bedding plane slip, so microseismicity with bedding plane slip signatures. So we think there could be both a small, brittle, but predominantly aseismic process which is occurring, and stress concentrations where we have this big change in geomechanical strength properties are an important part of that.
Yeah, exactly. So during some simulations, also I have shown that the criterion for fault reactivation can get to large values within those quick changes of properties, like right at the bedding plane, and it can lead to fault reactivation right there.
Yeah, so nucleate events right close to the bedding plane, and that could be what's happening with this cluster. So there were no large magnitude events here, but we're seeing a high event count very close to that interface.
Mm-hmm. Yeah, great, thanks.
All right, thank you, David, for addressing all these questions. And I believe there is not any other question from the audience. So I would like to thank you again for your time and for your interesting talk today.
My pleasure. Thank you.
Thank you. And thank you everyone for your interesting questions and for your time. Hope to see you next week.